2 degree of freedom forced vibration. Now we're going to look at what if we have more than 1 degree of freedom and we have forcing on the right-hand side. In the scope of this course, we are going to really limit the type of forcing we're going to be trying to find closed-form analytic solutions of. We're only going to be looking at simple harmonic motion on the right-hand side. We're only going to be looking at simple harmonic forcing on our right-hand side. For any forcing that's more complicated, we're going to rely on numerical solutions for this course, or in follow-up courses, you will see analytic closed-form solutions. So based on the equation of motion that we're going to look at, our left-hand side is now going to have a mass, a stiffness, and a damping matrix, and our right-hand side is going to have our force amplitude vector F times a cosine omega t. When we're looking at this simple harmonic forcing for our 2 degree of freedom and, as we'll see later, multi-degree of freedom systems, whether we have a C matrix that's the zero matrix or we do have damping and it's not the zero matrix, the solution procedure is going to look the same. Also note the right-hand side here, we have a force amplitude vector F, and that is being multiplied by the scalar cosine omega t. We are limiting not only that the force has to be a simple harmonic function, but also all degrees of freedom must be experiencing the same frequency, driving frequency, omega, and the same phase. So you notice on the right-hand side, there is no phase term there. They all must be in phase. Each degree of freedom can have a different amplitude of this forcing, and that amplitude could be 0, indicating that there is no external forcing acting on that particular degree of freedom. But again, if we have even a more complicated right-hand side than this, where maybe we have 2 different cosine functions acting on 2 degrees of freedom, or the 2 functions might not be in phase with each other, this solution procedure will not apply. So to find the solution to this system, we are going to be creating the impedance matrix, which we'll call Z. And Z is going to be calculated based on the stiffness matrix, the damping matrix, and the mass matrix. So notice that there's going to be an imaginary term if we have a non-zero damping matrix, which will cause Z to be a complex vector. If we don't have any damping, Z is going to be a purely real vector. And we're going to use this Z to find our steady state solution. And we're going to see the steady state solution for x of t is going to be this x times the cosine omega t. The steady state solution is going to be vector x times cosine omega t, where x is going to be calculated using the inverse of the impedance matrix times the force amplitude vector. So notice the limitations for this course on what we're actually finding. It's very specific forcing that's going to be involved, the same driving frequency acting on all of our degrees of freedom, just with different amplitudes, is the first restriction. And we are only finding the steady state solution for this course. We're not going to be seeing the transient solutions. In contrast with the 1 degree of freedom systems, we could have more complicated right-hand sides. We saw the transient solution and the steady state. We're not going into that much depth as we go into the 2 degree of freedom and then later multi-degree of freedom systems. Again, if we're interested in finding out more than just the steady state solution, if we want to know what happens in the transient phase, for now, we're going to need to rely on a numerical solution to see what happens then. Now notice we're going to have an issue here. When the impedance matrix is complex, that is, anytime we have damping in our system, then we're going to invert it, which is going to give us another complex matrix, and then we're going to multiply it by a real vector f, meaning that x, in the case where C is non-zero, not the zero matrix, x is also going to be complex. And if we look at how the steady state solution is formulated, at the moment it's going to look like we have some imaginary or complex term times a cosine omega t. That won't make any physical sense to have a complex coefficient in front of the cosine omega t. So we want to look at how to handle this situation where x is complex because z is complex. Well, what we're going to do is rearrange it And think of x when it's complex as being in Cartesian coordinates, having a real part and an imaginary part. And what we can do with it is, instead of expressing it in these Cartesian components, real and imaginary, we can express it in a polar form, where we're going to have a real part, kind of the radius of it, times an exponential to some angle phi. And we're going to be able to calculate the magnitude of x and this angle phi using imaginary algebra or complex algebra. So this phi is going to be calculated by the phase angle of the complex number. And the magnitude of x is going to be the magnitude, or the absolute value, of that complex number. So just like when we take the magnitude of a vector or the magnitude of any other complex number, we're going to find the absolute value by taking the square root of the sum of the squares. So it's the coefficient in front of the real part squared, plus the coefficient in front of the imaginary part squared, and the square root of that. That tells us the magnitude of this element of x. And then the angle is going to be just like we would find an angle for a vector with ij components. Here, the vertical component is going to be the imaginary part, and the horizontal component is going to be the real part. And in MATLAB or other programming languages, we're going to be able to use the angle function to find what the angle is. But really, all angle is doing, it's going to be taking the arctangent of the ratio of the imaginary part to the real part of our complex number. So again, we're essentially just converting from a Cartesian system into a polar system. So what's the utility of this, of expressing x as a polar form rather than a Cartesian form? Well, now we're going to be able to rewrite our steady state values in terms of only real components. So if we look at how it's rewritten now, in this case where we have 2 degrees of freedom, the steady state function for the first degree of freedom is going to be the magnitude of the first row, or the first element of that vector x. So that is what this x super 1 is. It's just talking about the first element of vector x. So its magnitude times the cosine omega t plus phi 1. So phi 1 is going to be the angle of that first element. And then the same idea for the steady state solution to our second degree of freedom. It's going to be the magnitude of the second element in x times cosine omega t plus the angle of the second element in x. So if we look at what the steady state solutions look like, it is just like what we saw when we were working with Bode diagrams in system dynamics, that at steady state, the solutions, or the behavior of our outputs, is going to have the same frequency as our driving frequency, omega in this case, but it can have a different magnitude and a different phase than our input. For this very limited case, the input on all of our degrees of freedom was that cosine omega t with some amplitude to it, f, and now our output we see has a different amplitude, x1 or x2, and it has a different phase, phi 1 and phi 2. And once again, this is only telling us about the steady state behavior of our degrees of freedom. We are not looking right now at the transient behavior.